SwayamPrabha. Digital India. Educated India.
Hello, in this video we will be looking at material symmetry available and how it helps to reduce the elastic constants in the stress strain relations. Continuing from the previous video, we started with a generalized Hooke's law for anisotropic material where there are 81 independent constants. We got it down till 21 considering both stress and strain symmetry as well as existence of a strain energy density function. But in this video we will see how we can further reduce it from 21 constants to all the way to 2 constants considering all the material symmetries. One major difference from the previous video and this video is earlier we were only looking at stresses at one single point in the material, but now we will be looking at what is the stress strain relation for any point in the material. So, that is when we get the material symmetries. So, which means until now we have not even touched upon what our materials, irrespective of the material we take, it gets down to 21 constants as was shown in the previous video. But in this video we will show if the kind of material we choose is a monoclinic material, then the independent constants reduce to 13. Further, if we consider the orthotropic material, the independent constants further reduce to 9, and later we will also discuss about transversely isotropic materials which has only 5 independent constants, and lastly the isotropic materials with 2 independent constants. So, let us start with these monoclinic materials. So, let us start with the monoclinic materials. These are materials where we have one plane of material symmetry. What it means is there is a plane where the points on one side of the material are simply the mirror image of the points in the other side of the material. So, since we have this mirror image across a plane, this plane, the normal to this plane is what we consider it as the principal direction. Since we only have one plane on which there is a symmetry, then we have only one principal direction to be considered. So, let us consider the coordinate system 1, 2 and 3. So, let us say this is 1, 2 and 3. So, these are 3 orthogonal coordinates, and then we will now consider another coordinate system where let us say 1, 2 is the plane of material symmetry, which means now let us take a different color and then show that this is 1 dash and 2 dash, meaning the 1 and 2 are repeating, but the third direction is opposite to 3. So, this we will take it as going downwards. So, these are the 2 coordinate systems, 1 dash, 2 dash and 3 dash is the second coordinate system, and the first coordinate system is 1, 2 and 3. So, now let us define the relation between stress and strain in the first coordinate system. So, there we will write as sigma ij in the first coordinate system is stiffness matrix C times the strain epsilon ij, again in the first coordinate system. Similarly, we can write the stress strain relations in the new coordinate system, which is sigma ij in the new coordinate system 1 dash, 2 dash, 3 dash is, here we will use the same stiffness matrix because the stiffness matrix is invariant with the transformation, but the definition of the strains are slightly different because these are in the new coordinate system 1 dash, 2 dash, 3 dash. Since the same stiffness matrix we are using in the first and the second coordinate system, this leads to some of the terms in the stiffness matrix going to 0. So, here we show those terms which go to 0. So, we will see that terms such as C14, C15 they go to 0, similarly C24 and C25 go to 0, C34, 35 goes to 0, and then these two components which are the C46 and the C56 going to 0. Since 8 of these terms go to 0, we are left with 13 constants. So, we started with 21 independent constants considering the symmetry in stress and strain as well as the availability of the strain energy density function. But now when we consider this monoclinic material, we got down from 21 to 13 constants. The same thing we can also show for the compliance matrix. So, for the compliance matrix again we see that it reduces to 13 constants. Okay. So, what we have achieved with the monoclinic material is these are materials with one plane of symmetry, and because of that one plane of symmetry we reduced it to 13 independent constants. Though we discussed here about the monoclinic materials, this has not much benefit when with respect to composites, because in components what we actually see is not just one plane of material symmetry, but a little more. So, we see more planes of material symmetry. So, what we actually see in most composites is there are 3 planes of materials that are orthogonal to each other and all 3 show the material symmetry. So, because each plane has a normal, so which means that normal we are now saying it as the principal direction. Since we are looking at 3 planes, then there are 3 normals and 3 principal directions. So, we have these 3 principal directions about which we have the material symmetry. So, let us look at a lamina. Here these directions 1, 2 and 3 we are saying are the principal directions, and then let us say that there are fibers, continuous fibers in this direction 1, and let us say the spacing of the fibers is equal in both directions 2 and 3. But what we will say is the spacing in direction 2 let us say is different from the spacing in direction 3. The reason why we are saying the spacing is different is just to bring this information that the properties in direction 2 are different in the properties in direction 3. So, that now we can make it more generalized. Okay. Now, if we assume this orthotropic material which has 3 planes of material symmetry, we show that few other components of the stiffness matrix go to 0, and what we end up with is this top right 3 by 3 matrix all going to 0. If you recall the compliance matrix we have seen earlier, we should remember that this top right square represent the shear extension coupling. So, what we are exactly showing here is there is no shear extension coupling. Additionally, what we can also show is if you notice this triangle, all these 3 components go to 0, and if you recall this triangle represented the shear coupling. So, we are saying that there is no shear coupling. Okay. So, we neither have the shear extension coupling nor the shear coupling. So, let us see what this implies. So, for example, let us say the kind of loading we are applying on this composite is sigma 1 is the only non-zero stress, which means the all other stresses are going to 0. The other 2 normal stresses like sigma 2 and sigma 3 going to 0, as well as the remaining 3 shear stresses, they all are 0. So, from this what we see is we only notice there is strain in direction 1 because C11 brings it, and then epsilon 2 and epsilon 3, all these are non-zero. We are not saying they are same, but these are all non-zero components. But because of these no shear extension coupling, all the strains or the shear strains are 0. So, which means gamma 23, gamma 31 and gamma 12, they are all 0. So, this says that if there is a uniaxial load, then we only see uniaxial strains. There is no coupling between extension and shear, meaning when we apply extension loads, there is no shear strains observed. Similarly, we can make another example, consider another example or an experiment, where we say the only non-zero stresses applied are, let us say tau 12 is non-zero and the rest all are 0. So, which means there is only one component of shear applied. So, if we apply a shear to this, what is the corresponding strains? We notice that except for gamma 12, which will be non-zero, all other strains go to 0. This is because again we have seen here it says that there is no shear coupling. Since there is no shear coupling, all other shear strains go to 0. So, orthotropic materials is of interest for us because most composites fall into this category, but we will see later that it can be further simplified under circumstances. Here I need to make a big distinction between what we call it as a specially orthotropic material versus a generally orthotropic material. So, earlier you remember we said there are 3 principal directions. So, these principal directions are coming from the material. For example, the directions of the fibers is one such direction and the other 2 could be perpendicular to the axis of the fibers. But the choice of the coordinate system is up to us. I could have chosen any 3 directions and said these are the coordinate systems for this body. But instead if I say the choice of my coordinate systems is same as the 3 principal directions which is coming from the material, then we have a special condition called the specially orthotropic. So, here we say the 3 principal directions are along the coordinate system, coordinate directions. Then we call it as the specially orthotropic, and in this special case that is when we get these shear extension as well as the shear couplings, they both going to 0. But there is another case where we say for the same material. So, here we are not changing the material, it is the same orthotropic material, but here you can see the coordinate systems which we have chosen is the new x, y, z. This is different from our principal coordinates which are these, let us say along these 1, 2, 3 shown in the left figure. So, now we see that the coordinate system we have chosen is different from the principal coordinates coming from the material or the principal directions coming from the material. When these 2 are different, the stiffness matrix we see is very different. So, we now see that there are no 0 components in the stiffness matrix, and in fact we see all of these components are non-zeros. So, now this might initially look a bit surprising because we are talking about the same material, it is the same orthotropic material, there is no change in the material. The only difference is the choice of the coordinate system. In the first case, this choice is aligned along the principal directions, and in the second case it is randomly chosen. When it is randomly chosen, we see that there are in this case we have 36 non-zero constants. But in this case, in the specially orthotropic where both the coordinate system and the principal directions are aligned, we only have these 9 non-zero components. Actually these are 9 plus 3, because of the symmetry we will have these components as well. So, this will be 9 plus 3 non-zero components. I do not want you to get confused. Here what we are again saying is there are only 9 independent constants. Because we know this stiffness matrix is symmetric, meaning these 3 components which I mentioned here, these are this C21, C31 and C32 are same as the symmetric components C12, C13 and C23. So, there are only 9 independent constants, but if somebody is asking you what are the total number of non-zero components, you should count these elements in the lower triangle as well, and then say these are actually 12 non-zero components. Okay. The take home message from this slide is, for the same material, depending on your choice of coordinate system, your stiffness matrix can have less or more non-zero elements. Usually a good idea is to go with the specially orthotropic, then the stiffness matrix is simple to handle. But of course, there are applications where you need to change the coordinate system, and we will later see how to do the stress or the strain transformations considering this change of coordinate systems. Now, let us look at a third category, which is named the transversely isotropic material. What it means is there is one plane where the material properties are the same in all directions. So, let us show it with an example. Let us say again we are discussing about the unidirectional lamina, where these are the directions of the length of the axis of the lamina, and then in this plane 2, 3 we have the fibers. Let us say usually in a lamina there are several number of fibers, and these are all randomly placed. Once they are randomly placed, and let us say this is a statistically random, what happens in this scenario is, let me show that cross section here, where we are saying that there are randomly placed fibers. This is the cross section we are saying. Because of the statistical nature of the randomness, if I pick 3 specimens from it, let us say these are the 3 specimens I cut out, one let us say is vertical, and let me call this as specimen 1, and the second specimen let us say is from the horizontal, and let us say I take a third specimen which is inclined. And once I cut these specimens out of the composite, let us say we are testing these along the direction. So, for the specimen 1 this is how we apply the loads, and for the specimen 2 we apply the loads along the length of the sample, and for specimen 3 again we apply the loads along the length of the sample. Because of this statistical randomness, we will notice that all 3 samples will show the same properties. So, that is exactly what we meant by the material properties are the same in all directions. So, which means the properties in the horizontal, vertical and in the inclined direction, in all directions the properties are the same, and this we are only saying about this plane 2, 3. So, if there plane exists where we have this symmetry, that is when we call the material to be transversely isotropic. Isotropic meaning the properties are same in all directions, but we are only saying it for one plane. Okay. If this is the case, then the stiffness matrix becomes much more simpler. Here we will notice that the direction 2 and 3 are immaterial, meaning both will have the same properties. For example, what we see here is C13 is replaced with C12. Similarly, here we have noticed the C55 is replaced with C66, and we also notice that C44 can be again written in terms of C22 and C23. And we also notice that C33 is replaced with C22, because we are simply replacing anywhere we see a 3 with a 2 and still we get the same properties. So, once we do these simplifications, we notice that it reduces to 5 independent constants. So, because of the transversely isotropic materials, now we had 9 with the orthotropic materials, but now that reduced to 5 independent elastic constant for a transversely isotropic material. And now we will look at the last category, and which we are more familiar with, which is the isotropic material. In an isotropic material, we have infinite planes of material symmetry, meaning like you take any plane, the properties are the same in that plane. Because of this symmetry, we see that the complete stiffness matrix can be written in terms of just 2 independent constants, C11 and C12, and all other components we see are written in terms of these 2 independent constants. So, similarly, here we have only shown the stiffness matrix. Similarly, one could show the compliance matrix, and again here too we will notice that just S11 and S22 are the 2 independent constants, but the rest of the terms can be written in terms of these independent constants. So, with an isotropic material, we have reduced to just 2 independent constants. So, this should summarize what we have discussed not just in this lecture, but even the previous lecture as well. So, we started with this generalized Hooke's law, which had 81 constants to define the relation between the stress and the strain, where we had 9 components of stress and 9 components of strain. But because of the stress symmetry, we reduced from 9 to 6 stress components, and then the independent constants reduced to 54. Sigma ij is equal to sigma j. Later, when we consider the strain symmetry as well, then we reduced it further to 36 constants. Later, when we showed that existence of the strain energy density function, we showed that the stiffness matrix is symmetric, that reduces it to 21 constants, not just for the stiffness matrix, but also for the compliance matrix. But in this video, what we have showed is we started with 21 constants for an anisotropic material, but when we started looking at the symmetries existing in the material, these constants decreased. For monoclinic, we said there is one principal direction or one plane about which the material is symmetric, meaning the other side of the material is just a mirror image across the plane. And for specially orthotropic, we said there are 3 orthogonal planes of material symmetry, and once we have that, it reduces to 9 independent constants. Later, we also discussed about this transversely isotropic, meaning there is one plane, in that plane the properties are the same in all directions. So, with that we reduced it to 5 constants. And lastly, with the isotropic, we said it has infinite number of material symmetric planes, meaning any plane you take, the direction the properties are independent of the direction. There we have further reduced it to just 2 elastic constants. So, this should summarize what we have been discussing in the last video and this video, saying that we are now able to define the relation between the stress and strain for not just for anisotropic materials, but other materials where there are symmetries. But to bring things in the context of composites, we are more interested in the specially orthotropic materials and the transversely isotropic materials. If it is just in a specially orthotropic material, we end up with 9 constants, but there are some composites where you can consider the transversely isotropic, that is when it reduces to 5 constants. With this we will conclude the video. In the next video what we will do is, instead of just showing it as some constants which does not have any physical meaning, we will try to bring in the engineering constant which has some physical meaning. So, we will try to rewrite the stiffness and the compliance components in terms of engineering constants which have some physical significance. Thank you and see you later.